we go to the next application of Navier-Stokes equation to viscous flows, where the flow takes place between two parallel plates and both of them are fixed. We call this as planar Poiseuille flow, as we have seen in the introduction. Flow between two fixed parallel plates. We have come across this geometry several times, though of course not telling the word Poiseuille flow. Okay. So, we have two plates, both of them are fixed. So, now when both of them are fixed, what drives the flow? In the earlier case, the top plate was moving, so that set the fluid in motion between the two plates. When both the plates are fixed, you need an external agency to make the fluid flow between the two plates. Okay. That is why second bullet says fluid motion caused by applying a pressure gradient, and that is shown little more practically here. We have the two plates which are fixed, and then you have an external, let us say a pump, which drives the liquid between the two plates. Okay. So, that is why we call this as fluid motion caused by applying a pressure gradient. This applied pressure gradient or this pump is which causes the flow between two plates. Okay. Now, and that creates a velocity profile between the two plates. Now, what is the practical significance of this example? Like we saw in the earlier case, the practical applications were viscometer and then shaft bearing, etc. Okay. Now, what is the application of this? I would say extremely practical example if the geometry were cylindrical. Okay. So, what we are discussing is a planar analog of flow through a circular pipe. Of course, throughout the industry, even household, we have a lot of pipes, they are all cylindrical. Okay. And what we are seeing is these two plates fixed, which is analogous to the fixed wall of the pipe. So, what we are discussing is in Cartesian coordinates, we are not discussing this flow through pipe, because that requires cylindrical coordinates. I have also shown a cylindrical shell here. So, that requires cylindrical coordinates. Okay. What is shown here is also a pressure driven flow, which means a pump pushes the liquid through the pipe. Okay. So, that is the actual practical scenario, a pump sending a liquid through a circular pipe. Instead of that, we are discussing taking two parallel plates which are fixed, because the pipe wall also does not move. Similarly, here also the two plates does not move, and so that is why we say it is a planar analog of flow through a circular pipe, and of course, both are pressure driven. When you say pressure driven, what you should understand is you have a pump which sends the liquid between the plates. Okay. And of course, you are going to consider laminar flow. We have discussed two flow regimes, laminar and turbulent, when we discussed about inviscid flows, which was our second level of application. So, here we are going to and that we saw inviscid flow happens at high Reynolds number, and now we are discussing the other extreme, this laminar flow. So, this happens at low Reynolds number. Now, in terms of the geometry, the two fixed plates are shown here and the axis is shown here, and like to mention the reason why we have chosen axis at the center. Okay. Y equal to 0 is at the center of the plates. Okay. Reason is that in the cuvette flow example, planar cuvette flow example, our axis x axis was here, and then y equal to 0 was at the bottom plate. Now, the reason for choosing this axis at the center line is that, remember, we are discussing this as a planar analog or Cartesian analog of the cylindrical pipe. For the cylindrical pipe, obviously, let us say r equal to 0 will be the axis of the pipe. So, we also like to choose a axis which is similar to the axis which you would choose for a flow through a pipe, flow through a circular pipe. That is why axis meaning y equal to 0 is chosen at the center of the plates. Okay. And so, in fact, in terms of expression also it look almost similar, whatever expression we are now going to derive for the velocity profile for this flow between the two parallel plates will be similar to the velocity profile which we would derive for a flow through a circular pipe. Okay. And of course, the fluid has property density rho and then viscosity mu. And now, what about the distance between the plates? The distance between the plates is 2h, but in terms of y coordinate, y equal to plus h here and y equal to minus h here, that should be kept in mind, because y equal to 0 is the axis. Okay. So, as in the last example, as in the case of planar cuvette flow, we will start with the continuity equation and we will assume the flow is steady. We will take the flow to be incompressible. Let us write the continuity equation and like in the earlier case we will consider flow only in the x direction. So, V x not equal to 0 and no flow in the y direction or z direction. So, V y 0, V z is also 0. Let us substitute in the continuity equation, V y 0 this term goes, V z 0 this term goes, and we have dou V x by dou x is equal to 0. The conclusion which we arrived for the planar cuvette flow as well, V x does not vary in the flow or axial direction, which we say is fully developed flow. Of course, V x can have a profile as a function of y, but the whole profile will not change in the flow direction. Now, we consider very wide plates. What do we mean by that? This is the width that is very wide, which means that there is no variation of the x velocity, V x does not vary in this direction. So, dou V x by dou z is equal to 0, which means that V x varies in the y or lateral direction only, dou V x by dou y is not equal to 0. So, we have V x as a function of y only. Okay. Now, we said V x not equal to 0, and by taking no flow in the y and z direction, based on the continuity equation we concluded there is no variation of V x along x, there is no variation of V x along x, and we made assumption that V x does not vary along z, and so leaves us with the condition that V x varies only along y. Okay. Now, if you look at this discussion, this is exactly same as what we did for the planar cuvette flow. There is no change. In fact, the same bullets are taken, in terms of text it is same, only the figures are changed. Okay. In both the cases, the conditions V x not equal to 0, V y 0, V z 0 and dou V x by dou x equal to 0, this assumption and this conclusion V x as function of y are all exactly same. Okay. Okay. Now, let us proceed to the Navier-Stokes equation. Let us state all the conditions, either assumptions or what we arrived from the continuity equation. Okay. So, steady state dou by dou t equal to 0, there is a velocity in the x direction. So, V x not equal to 0, no velocity in the y direction, z direction. From the continuity equation, velocity V x does not vary with x, V x does vary with y, V x does not vary with z. So, it is 0. Let us write the x component of Navier-Stokes equation, and the left hand side, because it is steady state, dou V x by dou t is equal to 0, and because V x does not vary with x, this term is 0, V y is 0, so this term is 0, V z is 0, so this term is 0. Okay. So, the entire left hand side vanishes. Let us come to the right hand side shortly. So, LHS, like in the previous case, of course assumptions are all same, okay. So, assumptions are made such a way that the acceleration term in the left hand side vanishes, both the temporal acceleration and the conductive acceleration vanishes. Okay. As I said, assumptions are made such that the left hand side vanishes. Okay. We also discussed what is the difficulty if you are not made such assumptions. If the transient term was there, it would have resulted in partial differential equation. The convective acceleration terms are non-linear, that is more difficult to solve. Okay. And so, left hand side becomes 0, exactly same as in the last case, no difference at all. Once again, this slide is also in terms of bullets, contents, it is same as last example except for the figure. Okay. Now, let us write the conditions. V x not equal to 0, V y equal to 0, V z equal to 0, and of course, dou V x by dou y not equal to 0, other gradients in other directions are 0. Now, we are going to look at the right hand side of the x component of Navier-Stokes equation. This is where the difference comes. Okay. And the first case, which is the planar cuvette flow case, there was no applied pressure gradient. So, there was no pressure drop along the length of the flow. In this case, this is where in fact we started the whole description. There is a constant applied pressure gradient which drives the flow. Okay. And as I told you, you have a pump which pushes the liquid between plates. Okay. And dou p by dou x is not equal to 0. In the earlier case, there was no pressure drop at all. So, the dou p by dou x was equal to 0 in the case of cuvette flow. In the case of Poiseuille flow, dou p by dou x is not equal to 0, pressure decreases along the direction of flow. So, in fact, dou p by dou x will be negative, because pressure will have to decrease along the flow, because it causes the fluid to flow between the plates, and hence there is a non-zero pressure gradient along the direction of flow. Okay. So, left hand side is 0 as we have seen in the last slide, right hand side of course gravity acts along y direction. So, rho g x is that term is 0 because g x is 0. In the earlier case this term was also 0, but now it is non-zero, minus dou p by dou x, that is a difference. And coming to the viscous stress terms on the right hand side, dou V x by dou x is equal to 0. So, second derivative is certainly 0, V x does not vary with z. So, second derivative is once again 0. So, we are left with only with this second derivative, dou squared V x by dou y squared, okay. And of course, we have mu here. Okay. So, let us write this minus dou p by dou x plus mu d squared V x by dy squared is equal to 0. Is it okay? So, that is the simplified form of the Navier-Stokes equation in the x direction. The entire left hand side became 0, right hand side we have the pressure gradient term and the viscous stress terms. Okay. Okay, let us look at the y component of Navier-Stokes equation. B y is 0, so the left hand side is 0, okay. And in the right hand side we do have the gravity term rho g y, of course we have the pressure gradient term, and of course the viscous stress terms are 0 because V y is 0. So, the y component simplifies to dou p by dou y is equal to minus rho g. Once again this particular part or the y component of Navier-Stokes equation is same as what we have seen for the planar cuvette flow case. Okay. Now, coming to the z component of Navier-Stokes equation, let us write down the conditions. Only x component of velocity is non-zero and only gradient of V x with y is non-zero. So, left hand side of the z component of Navier-Stokes equation is 0 because V z is 0, and in the right hand side there is no gravity term along the z direction, and the viscous stress terms are 0 because V z is 0, and this gives us the pressure gradient along the z direction to be 0. Okay. Once again this the z component of Navier-Stokes equation is same as what we have seen in the previous case of planar cuvette flow. So, let us summarize all the 3 Navier-Stokes equations. X component we have mu d squared V x by dy squared because V x varies only with y. So, it is a total derivative, and we have dou p by dou x on the right hand side. Okay. What does it tell you? It is a balance of pressure force and then viscous force. We have pressure force and then the viscous force, and the Navier-Stokes equation has got simplified to a balance of just pressure forces and viscous forces. Of course, both of them are net. Okay. We should say net pressure force per unit volume, net viscous force per unit volume, and y direction it is just a hydrostatic equation, and which is dou p by dou y is equal to minus rho g, and dou p by dou z is equal to 0. Okay. So, these are the simplified Navier-Stokes equation. Compared to the planar cuvette flow case, this equation is same, this equation is same. In the earlier case we had d squared V x by dy squared is equal to 0. In this case now we have mu d squared V x by dy squared is equal to dou p by dou x. Okay. So, because we have an applied pressure gradient and that is non-zero, our equation is slightly different from the previous case. It was just the second derivative was equal to 0, but now it is non-zero. Okay. Okay, now we will have to state the boundary conditions, and that is the equation we have. It is a second order ordinary differential equation. We need 2 boundary conditions to solve this second order ODE, and as in the case of the planar cuvette flow, we will use the no slip condition, and as I mentioned the no slip condition is an experimental observation which tells you that the tangential velocity of a fluid in contact with the solid surface is same as that of the solid surface. Okay. So, just to you will come across no slip condition very frequently, almost any fluid mechanics problem you take, you will come across no slip condition. So, let me repeat, if you in this case you have both the plates are fixed, what this condition says is the tangential velocity of a fluid in contact with the solid surface is same as that of the solid surface, and in this case both the plates are fixed. So, velocity of fluid layer just in contact with the bottom plate is 0, and velocity of the fluid layer just in contact with the top plate, that is also 0. In the earlier case at the top, because the plate was moving, we had a non-zero value. Okay. So, at the bottom plate which is fixed, V x is equal to 0, and what is the y coordinate? y is equal to minus h. Once again like to emphasize y equal to 0 is a central line, okay, and so the bottom plate is at y equal to minus h. At the top plate, what is y? Y equal to plus h, V x is 0. So, both at the bottom plate and the top plate V x is equal to 0.